Hello guys, today I'm going to talk about the useful name reaction, which is Buchwald-Hartwig cross-coupling reaction. You can also call it Buchwald-Hartwig animation reaction or BH cross-coupling or BH animation reaction for short. It's a chemical reaction that is widely used in organic chemistry for the synthesis of carbon-nitrogen bond mediated by a palladium catalyst. Although palladium-catalyzed carbonation couplings were reported as early as 1983, Stephen Buchwald and Joan Hartwig have been credited for its invention, and their publications between 1994 and the late 2000s established the scope of this transformation. Here is a bit background introduction about the two inventors. First, I will introduce you Stephen L. Buchwald, who was born in 1955. He's an American chemist and a professor of chemistry at MIT. He's known for his discovery of the Buchwald-Hartwig animation reaction and the associated ligand family for promoting this reaction. In year 2000, he was elected as a fellow of the American Academy of Arts and Sciences and also acting as a member of the National Academy of Sciences since 2008. Well, in terms of the other inventor, John F. Hartwig, he is also from the United States and a professor of chemistry at the University of California, Berkeley. His academic activities include the discovery and understanding of new organic reactions catalyzed by transition metal complexes and artificial metalloenzymes. He, of course, is also known for helping develop the Buchwald-Hartwig animation reaction. The successful establishment of the Buchwald-Hartwig reaction allowed for the faster synthesis of amines, replacing to an extent of harsher methods such as the Goldberg reaction, nucleophilic aromatic substitution, etc., while significantly expanding the repertoire of possible carbon-nitrogen bond formation. And then this is the general formula for the Buchwald-Hartwig animation reaction. The aromatic amine could be synthesized by coupling aryl halides or pseudo halides, for example, sulfonate with amines or amines. Well, the key feature of this methodology is the use of catalytic amount of palladium that is modulated by various electron-rich ligands. And also, the application of a spectrum of bases is essential to encouraging the effective takeover of the palladium catalyst. Well, to be specific, the halide could be aldyl, bromo, chloro, methylate, tosylate, or triflate. While the amine can be aromatic or alkyl, primary, secondary amine, or amide. You also have a wide range of options regarding the palladium catalyst and the associated ligands, depending on the coupling partners involved in those reactions. Here are some commonly used reagents shown here. For example, the palladium can be palladium-2, DPA3, palladium DPA2, or palladium acetate, etc. And ligand can be Z-phos, DPPF, breath-phos, Rufos, and S-phos, etc. With respect to the bases, you can use either inorganic ones, such as the calcium carbonate, potassium phosphate tribases, potassium carbonate, or sodium or potassium tributoxide, or some organic bases, such as lithium HMBS, which is a bulky and extremely reactive one that is only applicable at low temperature. And many other organic bases, such as triazamine and DBU, are also extensively used for this purpose. Well, in terms of the solvent, there are many alternatives also, including THF, DMF, terbutanol, toluene, and dioxin. Sometimes a little bit of water will be added to assist with the reduction of palladium 2 to palladium 0. Here we will go through the mechanisms. As the catalytic cycle shown here, first of all, you can use either palladium 2 or palladium 0 in the Buchwald-Hartwig animation reaction. However, if you use palladium 2, please be advised that palladium 2 needs to be reduced to palladium 0. That requires an amine bearing an alpha proton. Otherwise, extra ligand should be added to the reaction mixture to make the reduction happen. First, as aforementioned, sometimes a little amount of water is added intentionally to help with the reduction. For the next step, the palladium takes one ligand off and undergoes oxidative addition to form palladium 2 complex. After that, amine attacks palladium. You can also say it's a process of amine nucleophilic coordination, thus giving this tetracoordinated palladium species. Then the base assists with the deprotonation and dehalogenation, thereby affording this 3-coordinated palladium complex. Well, the final step is reductive elimination, where it yields the product and regenerates the monolactate palladium complex for the next catalytic journey. However, a side reaction that is beta hydride elimination can also occur in parallel to the reductive elimination. Then produces the RE and the corresponding imine. Fortunately, this unexpected side reaction can be avoided by the addition of deliberately designed ligand, on which I will elaborate a bit further in the next slide. So here it is the ligand part. Professor Buchwald proposed the general ligand design strategy as shown in this picture. In particular, the isopropyl groups in blue are designed for the purpose of increasing the stability of the palladium catalyst and stimulating the formation of monolactate palladium 0 species. The final ring marked green can prevent the oxidation of phosphine by oxygen, and meanwhile accelerate the reductive elimination, which is the final step of this catalytic cycle. So does the methox group on the other phenol ring in orange, which also help encourage the reductive elimination. Furthermore, the 2 cyclohexane groups on phosphine in red will promote both the oxidative addition and the reductive elimination throughout the whole process. And then why should the ligand be electron-rich? And what kind of jobs are they doing here? First and foremost, the ligands aid the reduction of palladium 2 to palladium 0 so as to kick off the catalytic cycle. Secondly, electron-rich ligands are needed to activate the palladium center towards oxidative addition, which is the first crucial stage involved in this reaction. And also, bulk electron-rich ligands are desirable to stabilize the monolactate palladium 0 species against the corresponding bi-identity palladium species. Besides, those ligands help promote the product forming step, that is the reductive elimination, and regenerate the monolactate palladium 0 catalyst. Other reasons for the application of electron-rich ligands are to enhance the enantiomer selectivity of the plant that we are after, and also inhibit the beta hydride elimination. So here are some representative ligands that was developed by the Buchwald group so as to meet some specific sensitive purpose. For example, the brake force as the molecular structure depicted here aims at coupling the primary amine, while the root force is designed for the secondary amine cross-coupling. Moreover, as known, the amine is not a good nucleophile, so more reactive ligand such as tributary brake force is assembled to solve this problem. So after giving you the basic information about the Buchwald-Hartwig animation reaction, right now I would like to share you some real-world application of this reaction. The relevant citations are also provided here for your reference if you want to take a closer look at these reactions. So because of the ubiquity of RE carbonation bond in pharmaceuticals and natural products, the Buchwald-Hartwig cross-coupling reaction has been frequently adopted in many organic photosynthesis and relevant industrial preparation of numerous pharmaceuticals. One of such applications was cross-coupling the chloride with aniline under conventional Buchwald-Hartwig conditions using palladium acetate, xanthos, calcium carbonate heated at 105 degrees in dioxin. As the chloride atom at the carbon 7 position was hard to displace, microwave-assisted heating was required from 1 to 5 hours. Then it provided the corresponding amine in a satisfactory yield. Then let's see the second example. The palladium catalyzed animation using 5-bromopyrimidine with different substitution groups at the carbon 2 position was carefully examined here. These bromides reacted successfully with 4-aminobenzonitrile and produced the desired amines in good to excellent yields. In these cases, palladium there was applied and xanthos was used as a suitable ligand, and sodium terbutaoxide was served as the base. In 2019, Chen and the co-workers developed this effective and useful method, as demonstrated here, for the synthesis of a wide range of nitrogen pyrimidine oxidizoles with Buchwald-Hartwig cross-coupling chemistry. Based on the optimal conditions, pyrimidines bearing a final group afforded the corresponding products in excellent yields as well. Moreover, in 2020, the Newman Group studied the Buchwald-Hartwig reaction using an easily accessible ligand, which was xanthos, together with DBU as a soluble functional group tolerant and homogeneous base. The reaction was detected to give amide in a satisfactory yield. This methodology was first examined by effective coupling 2-aldobenzonitrile, 2-bromopyridine, and 4-nitrochlorobenzene with different amides to give the corresponding desired compound also in good yields. Apart from the carbon-nitrogen bond formation, Buchwald-Hartwig chemistry also provides a reliable and general means for the coupling of RE halide or RE sulfonate with a variety of nitrogen, oxygen, and carbon nucleophile sources. Here is one of such examples. Starting from the dimethylchlorobenzene and primary amine, it gives the ether in 90% yield, which was pretty impressive. Of course, there are also many other examples regarding the carbon, nitrogen, carbon, oxygen, and carbon-carbon coupling under a wide range of Buchwald-Hartwig conditions. However, given the limited length of this video, it's impossible to cover all those types of reactions here. So I would like to leave it to you for further exploration. And then it brings us to the end of this short video. Thanks for watching. I hope you enjoyed it. And please feel free to leave some comments down below here to help me improve. Thank you.